to our class today. Today we'll be looking at simple AC circuit. Simple AC circuit. In order to discuss simple AC circuit, we need to understand the concepts that make up this topic. Of course, the word simple has to do with the basics of everything. The simple part of it, that is, those things you can easily achieve. That means that there are complex AC circuits. But at this level, our concern is on simple AC circuit. The basic thing that an AC circuit should have. So it is not a challenge to us. The concepts we are going to look at are AC and circuit. Beginning with circuit. What is a circuit? In the first place, what is a circuit? What is a circuit? A circuit is simply a path provided for the flow of electric current. That is a simple definition of a circuit. A path provided for the flow of electric current. So any medium provided, complete medium provided where electric current can flow comfortably is what we refer to as a circuit. And then we are talking of AC circuits. We have two classes of circuits based on the type of current that flow through them. We have the DC circuits and the AC circuits. We have the DC circuit and the AC circuit. The DC circuit stands for direct current circuit, while AC circuit stands for alternating current circuit. Now, I want to give us an analogy to differentiate between DC circuit and AC circuit. Let's take, for instance, you have a rechargeable lantern, or maybe your phone charger has 2-pin mouth. You will realize that if you want to plug it in an extension or a socket, there is no point of the mouth that is labeled positive, and there is also no point labeled negative. What you simply do is to plug it anyhow you wish to. Let's give a simple example of that. If I have this as a charger, this is not labeled positive or negative anywhere. Okay? But anyhow I plug it on a socket, it will work. So does it mean it does not have positive or negative? It does. So what then happens? That is because it is an AC circuit. Another thing, if you have experienced that if you get a battery, for instance, those days when we were small, we get a DC bulb, we'll connect 2 wires on it and plug on the battery, and it will on, and we'll be happy that we're doing wiring. Now, if you realize that if you do not connect positive to positive in that battery and negative to negative, it will not work. It will not power. That means that you must connect it in the right way for current to flow, and that is DC, direct current. But that of charger that I have explained is AC, because the current alternates. So what differentiates them? A direct current circuit is a circuit that current flows only in one direction, from positive to negative, while an alternating current circuit is a circuit that alternates its current. That is, it changes polarity. In 1 second, the left is positive, the right is negative. In another second, the right will become positive and the left will become negative. That is what happens in an AC, and that is why, however you connect, you will get your supply, because as it changes polarity, it gives you what you want. So that is just the basic difference between AC circuit and DC circuit. We'll not go deep into that because our concern is on simple AC circuit. Now, in discussing AC circuit, there are basic DC concepts that we are going to implement here, and those concepts are the concept of Ohm's law. We're going to apply it, even though it doesn't apply in every situation in AC, but it is going to even help us to get those situations that it does not apply. Okay, you remember that in your Ohm's law, that the relationship between voltage and current and resistance is that the current flowing through a metallic conductor is directly proportional to the potential difference between the two ends of that conductor, provided that temperature and every other condition is kept constant. And when we mathematically write it, we say that V is equal to IR, and that is a simple representation of Ohm's law. So this is going to help us a great deal to discuss AC circuit, even though It's not applicable in every instance. Okay, now when you come to AC circuit, the basic components we are going to take into cognizance are the resistor, the capacitor, and an inductor. The resistor, the capacitor, and an inductor. If you come to a circuit and you see something like this, it stands for a resistor. If you go to a circuit and you see something like this, it stands for an inductor. And then, I wrote capacitor here, so this should be capacitor. Capacitor is represented with this capacitor. And then if you see something like this, a coil, this is an inductor. Okay? The three of them opposes the flow of current in a circuit, but in different ways. Okay. Now let's look at these three components in a circuit and look at the different circuits that they exist. In an AC circuit, because we said that the current fluctuates, only resistor does not affect an AC circuit. The three of them affects it. So we'll look at several conditions of an AC circuit. Condition where the circuit is an R-only circuit. When I say R-only circuit, I mean a resistor-only circuit. That is an AC circuit that contains only resistor. In this kind of circuit, the circuit behaves like a DC because it has to obey Ohm's law, because the only opposition provided is the resistor. Okay, such circuit is represented in this form. You have this. This is the AC source, and this is the current. This is the resistance, and this is the AC source. So Ohm's law applied here. Now V is equal to IR. Okay, that is an R-only circuit. Another circuit you have in an AC is a C-only circuit. A C-only circuit. That is a circuit that contains only capacitor. And that is going to be like this. This is a capacitor, this is a supply, V, this is our current, and this is a capacitor. Now, by Ohm's law, V is equal to IR, but the resistance provided by a capacitor is not called R. The resistance provided by a capacitor is called reactance. So V is equal to IX, of course, subscript C, to indicate that it's for a reactance for a capacitor. To indicate that this is a reactance for a capacitor. I will explain better how this XC came here. But just note that V is equal to IXC, where X is the resistance provided by a capacitor. Then we also have a circuit that contains only an inductor. So we say L-only circuit. In an L-only circuit, we have only an inductor in that circuit. Okay, you have only an inductor, you have a current I, you have a voltage supply, and the inductor L. So this inductor provides an opposition. So if we follow what we have in Ohm's law, it will be V equals to I times the resistance provided by an inductor. And the resistance provided by an inductor is also called reactance, but that of inductor, reactance of an inductor. And we have V is equal to IXL. So looking at these are the individual components, three basic components we have in an AC circuit, and when they are represented in this AC individually. So we are going to look at a series combination of two or any two of them or three. But before I want us to look at that, I want us to have a definition of this thing: resistance and reactance and impedance. There are the three names we have to represent resistance offered by these components. We have the resistance, we have the reactance, and we have the impedance. Okay, we have the resistance, reactance, and impedance. Resistance, number one, resistance. This is the opposition provided by a resistor in a circuit. This is the opposition provided to the flow of current by a resistor in a circuit, and it is measured in ohms, represented with capital letter R. The reactance is represented with X, still measured in ohms. But reactance is not provided by a resistor. It is the opposition provided by either an inductor or a capacitor or both to an AC circuit. Remember I said that the opposition provided to an AC circuit is either done by a resistor, an inductor, or a capacitor. So the opposition provided to an AC circuit by an inductor or a capacitor is reactance, while that provided by a resistor is called resistance. So this reactance is the opposition provided by either an inductor or a capacitor or both to an AC circuit. Then impedance. Impedance has to do with a combination of resistance and reactance. It has to do with combination of resistance and reactance. Okay? If you combine resistor and any of these reactants, that is resistor and inductive reactance, or resistance and capacitive reactance, you get what you refer to as impedance. So either once there is resistance and any of these two or both, we have impedance. So impedance is the opposition provided by a resistor, an inductor, and or a capacitor to an AC circuit. So if the opposition is provided by, I said again, a resistor and any of inductor, capacitor, or both, you call it impedance. So these are the three positions: resistance, reactance, and impedance. The three of them are in ohms because they are resistance. Resistance is represented with R, reactance is represented with X, and impedance is represented with Z. Reactants are of two, which I have said initially that the reactance XL is the opposition provided by an inductor. That is, we call it inductive reactance. We call it inductive reactance. Okay? Inductive reactance. While that is the opposition provided by a capacitor to an AC circuit is called capacitive reactance. Capacitive reactance. And then that provided by a resistor is called resistance. So putting these three things together in a circuit, we have looked at them individually, how they exist in a circuit and the relationship between them and Ohm's law. Now, before we begin to look at the combination of any two or three, we want to look at the actions of these three components in a circuit. That is the three of them put together. Okay? If you have a circuit that contains the three components, a resistor, an inductor, and a capacitor, let us see how the circuit looks like. Okay, we have this, a resistor. Remember, I have shown you the symbol to represent the three of them. We call this circuit that contains the three an RLC circuit. Yes. Where resistance, inductance, and capacitance are put together. Please don't confuse a capacitor with a cell. They look alike, but they are not the same. In capacitance, the two polarities are equal, but in a cell, one is longer than the other, where the longer one represents positive and the short one negative. So this is a capacitor, this is a cell. So don't confuse it. So we have inductor, resistor R, inductor L, and capacitor C. If you put these three components in one circuit, one AC circuit, this is what is going to happen. Now, the current that is going to flow through this circuit, you know, is a common current. It's going to flow through because it's a series circuit. We also have a connection of RLC in parallel, but it is not in our scope. So we are going to concentrate in series connection. So if current flows through this series connection, the same current that passed through R will pass through L and will pass through C. So because of that, they have a common current. And the voltage supplied V. Okay, the voltage and the current that will pass through this resistor will be in phase. That is, they will be at the same side of the vector. So if this is the voltage for R for the resistor, and this is the current, of course the current I said is a uniform current, so we don't have current for resistor, the same current that passed through the three of them. Then the voltage that is going to drop across this inductor is not going to be in line with the current, because this inductive reactance is not a pure resistor. So the voltage that is going to drop across the inductor is going to be leading the current. So we have VL like this. So we can say that the current is lagging behind the voltage of an inductor by 90 degrees. Okay, the current of and the voltage of a resistor are in phase. I repeat, the current and voltage of a resistor are in phase, while the voltage of an inductor leads the current by 90 degrees, or alternatively, the current of an inductor lags behind the voltage by 90 degrees. Okay, then that of a capacitor, the voltage that will drop across this capacitor is going to be below the current. So it means the current of a capacitor, the current of a capacitor leads the voltage of that drops across the capacitor by 90 degrees. Let me just recap again. The voltage and current in a resistor are in phase. The current in an inductor lags the voltage of an inductor by 90 degrees, while the current of a capacitor leads the voltage across the capacitor by 90 degrees. So this is what we refer to as a vector diagram of an RLC circuit. This diagram now represents a vector diagram. And remember, in your vector, if we want to resolve this thing into one, to have a resultant, we have to pull the three of them as one, to have a horizontal component and a vertical component. Of course, we already have a horizontal component, and then we have two vertical components that are in opposite direction. So we're going to put the two of them together to form one component. Remember, these three things can be represented as the vertical and the horizontal. So if this one is going to be made, the VC is going to be made to join VL, because it is no opposite direction, we have VL minus VC. This is the vertical component. While the horizontal component is VR. Okay, so if we consider this, what is going to be the resultant? The resultant, which is V, using Pythagoras theorem, is going to be V equals opposite over, is going to be V squared by Pythagoras theorem equals to opposite squared plus adjacent squared equal to hypotenuse squared. The V is the hypotenuse, equals VL minus VC squared plus VR squared. You can write VR first before this, anyhow you want to do it. So V is equal to the square root of VR squared plus VL minus VC squared. Okay, this formula now is what we will get used to determine the resultant voltage that flows through a resistor, an inductor, and a capacitor in series. Okay, but we know that voltage stands for current times resistance. So I can say that this V is I times the total resistance, which is the impedance as we described for the three of them. Okay, because the three of them are in the same circuit. And that is equal to the square root of, this one is I squared, the same I because it's the same current that flows through the circuit, I squared times R squared, plus this one is going to be the same I, so I can bring out I squared times XL minus XC squared. Okay, and because these two currents are common to these two terms, we can factor it out to have that IZ equals the square root of I squared bracket R squared plus XL minus XC squared. Of course, this square will cancel the square root so that this current will come out. And then we'll have mathematically that IZ equals I square root of R squared plus XL minus XC squared. And this I can cancel this I. So impedance is equal to the square root of R squared plus XL minus XC squared. This is impedance. So we can use this. You can see that this and this, they are related. When you are, the resultant voltage for an RLC circuit is this. The resultant or the total resistance for an RLC circuit is this. Okay, that's the relationship between the resistance, inductive reactance, and capacitive reactance. Okay, we have defined the three components, but the vector diagram as well, we can represent the vector diagram using this. So instead of voltage, I can just put XL here minus XC here. This will now be impedance Z, and this will now be R. So it's still the same thing. Whether you use voltage or resistance, this remains a vector diagram. Okay. One thing we should also note is, how do we get this XL? How do we get this XC? Because in a question you could be given the inductance and the capacitance, not the inductive reactance and the capacitive reactance. Remember, they have their units. Resistance is in ohms, inductance is in Henry, while capacitance is in Farad. So these are the units of this component. But because we call them resistance, when this is converted to resistance, which is XL, it becomes ohms. When this also capacitor is converted to resistance, which is XC, it also becomes ohms. The question is, how do you convert inductance and capacitance to inductive reactance and capacitive reactance respectively? They have their formula. So the inductive reactance is affected by the frequency 2 pi FL. It is directly proportional to the frequency, and the inductive reactance is directly proportional to the frequency and inductance, while the capacitive reactance is inversely proportional to the frequency and the capacitance. Okay, so inductive reactance is 2 pi FL, while capacitive reactance is 1 over 2 pi FC, and 2 pi F is the phase angle, that is omega L. This can be represented with omega L. This can be represented with 1 over omega C. That is how we are able to get the inductive reactance and capacitive reactance. Okay, if we have achieved that, so we can see the relationship graphically. We want to represent these three components. You call this the resistance. How are they affected by frequency? Because the frequency in a circuit might not be constant, it might be fluctuating. How does it affect the resistance, the inductance, and the capacitance? As we can see, the frequency is what is used to determine the inductive reactance. It is also frequency that is used to determine the capacitive reactance. So it means that frequency has impact in them. Okay. Now, but you see that resistor has nothing to do with frequency. That means that the frequency fluctuation does not affect the resistance. Does not affect resistance. So whatever the resistance is here, it remains the same even with a varying frequency. That is how, if this is a graph or how you represent the resistance and frequency, the relationship between the resistance of a resistor and frequency. Then if it is inductor, you see that the inductive reactance is directly proportional to the frequency, and that means that inductive reactance, if the resistance is reactance, this is a direct proportional relationship, XL. That is, as the resistance is increasing, as the frequency is increasing, the resistance of an inductive reactance increases. But like I said, it does not affect the pure resistance of a resistor. The pure resistance of a resistor remains constant, even with varying frequency. But for an inductive reactance, it is directly proportional to the frequency. While for a capacitive reactance, you see the capacitive reactance is inversely proportional to the frequency, and we have a curve type of graph this way, where this is the capacitive reactance. Okay, this is a graphical representation of these three components of an AC circuit. While the other one we drew is a vector diagram, so you should know their differences. So if you look at this graphical representation, you will see that there is a place where the inductive reactance coincide with the capacitive reactance. Okay, and if you look at this formula, if you are mathematically inclined, you understand something, that if XL becomes equal to XC at this point, these two things will go, because if they are equal, they will subtract each other and become 0. And if 0 squared is still 0, that means this will be the only thing remaining. And you know, this square root will cancel this square, and we have R. So Z will be equal to R. So at that point where the total resistance in the circuit that contains the three components, a resistor, a capacitor, and inductor, but the only one that is active is the resistor, at that point, the frequency at that point is referred to as resonance frequency. The frequency at the point where the inductive reactance is equal to the capacitive reactance, and of course the total resistance in the circuit becomes the resistance of the resistor. That frequency at that point is called resonance frequency, and at that point is where resonance occurs. So at that point, the circuit allows maximum current, because the only resistance, the only opposition it now has is the resistor. The capacitor and inductor has cancelled each other. So this frequency is referred to as resonance frequency. And from what we have here, we'll be able to get a formula to determine resonance frequency. At resonance, we say that XL is equal to XC. So someone can actually say that at resonance, 2 pi FL, where F is resonance frequency, equal to 1 all over 2 pi F resonance frequency C. And then when we cross multiply this to make resonance frequency the subject of the formula, we have 4 pi squared F naught squared then LC equals 1. And when we divide through by every other thing apart from F naught squared, because that is what will be the subject of the equation, F naught squared will be equal to 1 all over 4 pi squared LC. Okay? So if we now want to get the square root of F naught so that it will be alone, F naught will be equal to the square root of 1 all over 4 pi squared LC. And if we take them one after the other according to the third law, the square root of 1 is 1 divided by the square root of 4 is 2, the square root of pi squared is pi. But we cannot determine the square root of L and C, so they should remain with the root. So this is the formula that is used to determine the resonance frequency of an RLC circuit. Okay, this is the formula to determine the resonance frequency of an RL circuit. You should take cognizance, take note of this formula, because it's going to help us in solving questions. Okay, so at that point, like I said, if you ask what a resonance frequency is, it is the frequency in an RLC circuit where the capacitive reactance is equal to inductive reactance, and at that point the current flowing through the circuit is maximum, because the only opposition that occurs is the opposition provided by a resistor, because that of the capacitance and inductance has cancelled out. So we should note that. If we have understood this, then in order to solve questions applying to these three components, we also note that we have what we call there are three currents and voltage that exist in an AC, unlike a DC circuit. There are three currents and voltage that exist in an AC circuit, unlike a DC circuit. In a DC circuit, current is current and voltage is voltage. But in an AC circuit, we have what we call peak. Let's say for current, we have peak current represented with I. We have instantaneous current represented with, peak current represented with I naught, instantaneous current represented with I, and then root mean square current represented by IRMS. The same thing applies to voltage. We have the peak voltage, which is V naught. We have the instantaneous voltage V, and we have the root mean square voltage V RMS. And these three components have their relationship. These three voltage and current have their relationship, and they represent something in an AC circuit. The peak current is like the maximum possible current that can exist in an AC circuit. If you realize, if you have done an experiment putting maybe a multimeter or a measuring instrument into a circuit or an extension, an AC supply, you realize that the multimeter does not stay steady. It does not become steady because the current fluctuates. And because it fluctuates, because there are ripples in the AC, because it fluctuates, we cannot say that the voltage is this or the current is this. It begins to change value. But amongst all the values that it changes, if you watch for a while, there is a particular value that this fluctuation does not exceed. This particular value that it does not exceed is the peak, if it is current, peak voltage, if it is voltage. Then instantaneous current is the current at an instant of time. Instantaneous voltage is the voltage at an instant of time. Then root mean square current and voltage is that current or voltage that provides the same heating effect as is DC equivalent. So that thing that is naturally would have provided if it was a DC, that is what we refer to as root mean square current or voltage. That voltage or current that the circuit would have provided steadily without fluctuation, assuming that circuit was a DC, is what we refer to as root mean square and the current and root mean square voltage. How are they related? They are related that the root mean square current, that is RMS current, is equal to peak current all over root 2, which can be written as 0.707 I naught. So the root mean square current is equal to 0.707 peak current. The same thing applies to voltage. The root mean square voltage is equal to peak voltage all over root 2, which is also equal to 0.707 V naught. Okay? Then the instantaneous current and voltage also has a relationship with the peak current and the voltage. The instantaneous current is equal to the peak current sine omega t, while the instantaneous voltage is equal to the peak voltage sine omega t. So let us take note of this. So if you are to determine, maybe in an only R circuit, if you are determined to determine the root mean square voltage, you should know that it is going to be the root mean square current times the resistance. You cannot use the peak current to determine the root mean square voltage. So if you are given the peak current, you have to first of all use the peak current to get the root mean square current before you can now use it to determine the root mean square voltage. The same thing applies if you want to determine the peak voltage. It is still going to be the peak current times the resistance, depending on the kind of resistance, whether it is a pure resistance of a resistor or an inductive resistance, capacitive reactance, or impedance, whichever one. If it is impedance, the V root mean square will be equal to I root mean square then Z. Okay, so whichever one it is, these are the relationships. So with this, we have been able to explain or create a background to an AC circuit. In our subsequent video, we are going to solve series of examples on this from WAEC and JAMB, so that you see how we apply these things that we have explained so far.